This is the precalculus course. My name is Xiaosong Wang, and the lecture is prepared based on this book, Precalculus, Mathematics for Calculus by Stewart, Redding, and Watson, 6th edition. This is the publishing year and publisher's information. Our first lectures is the fundamentals of first part. Okay, we deal with review some high school mathematics and to set up and unify terminology for this course. We're talking about real numbers, exponents, radicals, polynomials, and their rational expressions. Okay, first, the number system, we use n to represent the set of all positive integers, and z to be the set of all integers. Q is the set of all rational numbers, and R is the set of all real numbers. And we don't talk about complex number in this course. Okay. In R, we have two arithmetic operations, addition and multiplications. You may wonder what happened to subtraction and divisions. We'll discuss those things later. Okay, they satisfy the following properties for additions and multiplications. The first one group is we call it commutative properties, which says a plus b equal to b plus a, which means we can switch order of the additions, and for multiplications, it equals to a. It means a times b equals to b times a, and the second group is called the associative properties. Here, a plus b first inside of the parentheses, then we add c, which equals to a plus b plus c between the parentheses. Here is the quantity. We add them first. Okay. Once this equality holds, which means we can forget the parentheses. And for multiplications, we have the same thing. A times b, then times c equals to b times c first, then a times this quantity. Okay. The third group is called the distributive properties, which combine the addition and multiplications. The first one is a times b plus c equals to a times b plus a times c. This one is called the left distributive properties because a is on the left term of this multiple. Okay, the second one will be called the right distributive property, which is a plus b first, then multiply c equals to a times b plus a times c. Okay, and here's an example for the notation manipulation. We get a plus b times c plus d. Okay, first we're fixing the second quantity here and use the left distributive property. I'm sorry, the right distributive properties to get this, and then the left distributive properties to each individual term, so we get that. Okay, what about, now we answer the question about the subtraction and division. Okay, for subtractions, we means a minus b equals to a plus negative quantity of b. Okay, and for division, we a divided by b equals to a times the reciprocal number of b, which is 1 over b. Okay, and we write it as a over b. Of course, when we have division or denominator number here, it cannot be 0. Know that we can associate real numbers with points on the line, or any points we can associate it with a real number. So here are some notations about the sets and the intervals on the real lines. I'm going to show you by one table. Here is the open interval AB for notations. Use open parentheses, and the set theoretical notation is the collection of all real number x. X lies between x is strictly smaller than a is strictly less than x, and x is strictly less than b. And for graph, we just put on the real line, and A and B, we use the open dot to represent that the interval, the endpoints are excluded in this set. And the second one is the closed interval A and B. We use the bracket notations to represent that the endpoints are included in this set. Okay, over there, you use the solid dots in the graph, and here are these two are the half open intervals. This one is the left close, right open, and this one is the left open, right close, and use the notation a to infinity to represent the open ray. So it goes to right infinitely. Okay, and we only have one endpoint A, which is excluded in our set, and we use the close bracket to represent the closed ray. And this one use the open ray, but right now the ray points towards the left-hand side of the real line, and we use this one to represent the closed ray pointed towards the left. And the whole real lines, we use the open interval negative infinity to infinity to represent the whole real, the set of all real numbers. Okay, and here is one more notations for the union of two disjointed open intervals. Okay, one remark, the infinity sign is just a notation. Okay, it is not a number about the absolute values and the distance on the real line. For absolute value, let A be any real number. The absolute value of A is this. We define it to be when A is a negative number, the absolute value of A is A. Okay, if A is negative, the absolute value of A is minus A or negative A. You see, because A is negative, negative A becomes positive. Okay, here is a simple example. So for the absolute value of square root of 2, plus or minus, after we take the absolute value, which becomes the square root of 2. Okay, for distance, for any 2 points or any 2 real numbers, which they also can be viewed as 2 points on the real line, and we define the distance between them to be the absolute value of A minus B. Here's a simple example. The distance between -3 and 5 equals to the absolute value of -3 minus 5, and which is -8. Then take the absolute value, and so we get the distance between -3 and 5 equals to 8. Okay, next topics will be the exponents. Okay, let A be a real number and n as a positive integer or natural number. Then we define the nth power of A to be, we just multiply A n times. For terminology, we call A to be the base number of this exponent notations. And n is the exponent. Okay, next we try to generalize the exponent notations to with exponent n to be any integers. So first, we have to assume the base number. To do that extension, we have to assume the base number is not 0. Okay, for n, so we define a to the power of 0 equal to 1. Okay, remember that the base number a cannot be 0, and we define a to the negative n power equals to 1 over a to the power of n. That's how we define when the exponent is as a negative number. Okay, remember that in the beginning, n is a positive integer, so which is also equals to 1 over a to the power of n. Okay, let's show you a few examples. So putting somewhat exotic base number, negative pi to the power of 0, whatever the number, a base number is. Okay, as long as it's not 0, we get equals to 1. And next example, we show you a negative power 2 to the power of negative 3 using that notations, which equals to 1 over 2 cubed. Okay, you might do the calculation in your mind, you get 8 over there, but just play with notations. It also equals to 1/2 cubed. Okay, and it is this. So that's the result, equals to 1 over 8. And one more example, 3 to the power of 4 equals to just 3 multiply 3 multiply 3 multiply 3. 4 times you get 81. Do the notational manipulation. Actually, it also equals to 1/3 to the power of negative 4. The law of exponents, okay, they satisfy some properties. Okay, here A and B represents the base number, and m and n are any integers. Okay, they use them to represent exponents. Then we have this. The same exponent, the same base number and different exponent, their multiple equals to the same base number of exponents. We just add them up. On the other side, we have some examples. And a to the power of m over a to the power of n. So we equals to, we just subtract them. Subtracted exponents of the denominator, and a to the power of m to the power of n equals to just multiply the exponents, and here is a times b to the exponent to the power of m. We can just take the individual exponent separately, then multiply them. Okay. For the division, we have this negative power. What's the difference between this one and the previous definition for negative integer power? Here, the difference lies on the fact here is that we are allowing m to be any integers. So m can be even negative numbers. Okay. Left-hand side are some number examples. Okay, it should not be too difficult to convince yourself they are correct. Okay, here's the question about associative laws about parentheses. So my question is, a to the power of b to the power of c equals to a to the power of b. Put them between parentheses, then take the power of c, or put the pair of parentheses on the exponents, and the answer is this. It should be this one. Okay, because this quantity should becomes a to the power of b times c instead of exponent. You see the difference here? Okay. About radicals. Okay. So the purpose of this is we try to expand the exponent notations for exponents to rational numbers. So we define n, let n to be any positive integers, and the principal nth root of a is defined, or the nth root of a can be written as a to the power of 1 over n and equals to b, and the quantity b is to be chosen this way. Okay, means that b to the power of n equals to a. Okay, there's a danger here is that if n is even, then and we must assume that the base a number must be a negative, and we choose even number roots of a to be also a negative number. That's why we put principal nth roots over there. Okay, and all the exponent laws in the previously we have now hold also true for rational exponents. Okay, here are a few examples. The square roots of -3 squared equals to 3, which is also the square roots of 3 squared. And we are using a much more general facts over here. The nth roots of a to the power of n equals to the absolute value of n a if n is an even number. Okay. The second example is the cubical roots of the fifth root of 2. Okay, try to do this. Before we do that, we are going to change it to the exponent form of rational exponents, which is this. 2 to the power of 1/5 to the power of 1/3. And then we can use the law of exponents, simply multiply this quantity 1/5 and 1/3, and which is equal to 2 to the power of 1/5 times 1/3, and which is 2 to the power of 1/15, and they can also put into these two different forms. Okay, third example is we try to rationalize this quantity because it's the purpose here is we try to rationalize the denominator. Okay, here this quantity here, 2 over the cubical root of 3. We have a cubical root of 3 in the denominator. We try to the goal is try to do something about the denominator to make it becomes integer. Okay, and to do that, we have to multiply something in the denominator. To do that, without changing this quantity, we also have to multiply something in the numerator, and which is here is what we do. We multiply the cubical root of 3 times 3 squared upstairs and downstairs. So we have the same equality. And the reason we choose this quantity to multiply is that once we multiply these two things, we can have nice looking numbers in the denominator. Okay, so after all these equalities, we rationalize the denominator and put the nested term in the numerator. Okay. And for algebraic expressions, we have some identities to discuss. Okay. The first one. Before that, we introduce polynomials in the variable x, and which is the expression of this form: an times x to the power of n plus an minus 1 to the power of x times x to the power of n minus 1 plus to a1 plus times x plus a0, and here a0, a1 to an are the real numbers, and n is any non-negative integers. Okay, if the leading one, okay, an is not 0, we call the polynomial of degree n, and each individual term we call the monomials, and they make up the terms of the polynomials. One thing to pay attention is that we are matching the exponent with the subscript of the coefficients, so it's sometimes it's easier for us to deal with the problems. Okay, so we define the algebraic expression, which is specifically reserved for real coefficient polynomials. And here are some examples. We try to add and subtract polynomials. The first one is we add two polynomials. The first quantity is we add this polynomial of degree 2 and degree 3. And the second one is we try to add, it is a quadratic polynomial or polynomial of degree 2. And by using the associative law and the commutative laws of addition, so we try to rearrange the terms of the matching coefficient, the degrees, then add them up, and so which is this. Hopefully it's not too quick for you. It should not be too difficult. So all these techniques are used in, say, junior high. And second one is do the subtracting of two polynomials. And this time, because I try to match what I did before, subtraction equals to what plus negative of that. And so that's what I did here, plus negative of the second quantity. Then I use the distributive properties to multiply -1 to each individual term, which becomes this. And next, I rearrange terms to the descending order. I put the highest degree terms in the first, and the second one is I try to group the same degree terms together, which is x to the power 5, and we have one here and one over there, and just copy down the remaining one. And the last one is we have two scalar terms. Okay, so here is the end result. Okay, then we talk about some algebraic identity formulas. The first one is a plus b times a minus b equals to a squared minus b squared. This identity is called the difference of two square quantities. Okay, we are going to use them quite often later. And the second group is the sum of two square and the difference of two square, which equals to, first one is the square of a plus b equals to a squared plus 2ab plus b squared. And the second one is a minus b squared equals to a squared minus 2ab plus b squared. And the left-hand side of these two quantities are called perfect square, okay, or the difference, the square of difference for the third one, and the second one is called the square of the sum. Okay, we are going to use them quite often too. Okay, the fourth identity and the fifth one, I show them together. They are called perfect cubes, or the first one is called, because they are a quantity of some cube, the cube of some quantities. Okay, the first one is also called the sum of the cube of the sum, and the fifth one is called the cube of the difference. Okay, and here they are. And the sixth one is this, a plus b times a squared minus 2a minus ab plus b squared equals a cubed plus b cubed, which we also call this identity the sum of 2 cubes. And you might be able to imagine that the seventh one will be the difference of 2 cubes, which it is. The difference of 2 cubes equals to a minus b times a squared plus ab plus b squared. Okay, and we call all this identity, if we do it from the left-hand side to the right-hand side, we call it expanding. We multiply them out. Okay, and we call a typo here, from the right-hand side, from the right-hand side to the left-hand side, we call it factoring. No typo, sorry. Because I put the arrow in different directions. Okay, and both directions are of equal importance in our techniques of studying these quantities. One more remark about, for practical reason, the fourth one to the seventh one are the only thing you need to know about treating cube quantities. Okay, for higher order exponents, you should not worry too much about them in this course. Okay, and the question I'm asking here is, what can the quantity A and B are? Okay, we try to use the principle of substitutions. Okay, so to answer this question, let's see the proof of all these quantities. So for the first one, okay, I starting with the left-hand side, I try to multiply this out to get to the right-hand side. Okay, so first I'm going to use the right distributive property, which means I try to multiply this quantity by fixing the red number, the red color terms, a minus b. So fixing this, treating this one as a whole, we multiply them, which becomes a times the quantity a minus b plus b times the quantity a minus b. And then we use the left distributive property on each individual term, which becomes a times this, a times that, minus a times b plus. The second one is I multiply them out, which is b times a minus b times b. And I can rewrite this a times a into a squared, and this quantity becomes b squared. And pay attention to the middle one. The first one is negative minus ab plus ba. Next step is I try to switch the order of this multiple here to make it becomes a times b. So I'm using the commutative properties of two algebraic quantities A and B. And after I switch order, I can cancel them because one is negative, the other one is positive. So the end result equals A minus B. And the second one I will leave you as an exercise. And the third one, I'm going to prove it using the sum of two squares. Again, the second equality, which is the square of the sum. And now we are trying to derive the square of the difference using the square of the sum. So I have to change these notations from negative b, minus b to plus negative b, which is this. Okay, then apply the second identity. Okay, the square of the sum, which is a squared plus 2a times negative b plus negative b squared. And this quantity, as you can see, a perfect square. So with or without negative sign, it will be the same. And about these quantities, I can move the negative sign to the front, and it becomes the end result. And the remaining ones are left as also left as exercises. And now we are ready to answer the question posed in the previous page, which is what can A and B are. Here, let's carefully examine this one. We are using the distributive property and commutative property. So as long as the quantity A and B satisfy all those identities, the laws, okay, they can apply. And for now, the numbers or the algebraic expressions, the polynomials for now, and hold true for by using the principle of substitutions. That is, as long as the A and B are numbers or polynomials, okay, we can apply all these identities. Here are some expanding examples. First one is we try to apply the square of difference, the difference of two quantities. The first one is 3x, and the second quantity is the square root of 2. And we apply the square of difference formula to get that. Okay, then let's rearrange terms, put the scalar term into a nicer form, use the law of exponents. You see, we have, for this one, we have 3x squared. So use two different base number, and the first one we get, it becomes 9 to the x squared. 9 over there is 3 squared. And here I'm going to use, for the second quantity, 2 times 3x times square root of 2. I'm using the commutative properties and associative properties to put the scalar term to the front, and it becomes negative 6 square root of 2 times x. And for the scalar terms, square of square root of 2 equals to 2. This should not be too difficult. Okay, and the second example is this. I try to multiply the quantity of 2x plus 3y plus 1, okay, times 2x plus 3y minus 1. Of course, you can use the distributive properties to do the expanding directly. However, I'm going to use slightly different techniques, because by observing that we have 2x plus 3y over here, and we also have 2x plus 3y y over there, and we have plus 1, and we have minus 1 there. I can use, so all of them have different quantities. So I'm going to use the difference of 2 square formulas identities for this, which becomes 2x plus 3y squared minus 1 squared. And next, I'm going to expand the first term using the sum of square form identities, okay, which becomes this. And 1 squared is 1. So keeping the scalar term. And next one, also I try to rearrange, to simplify this quantity and this quantity and this quantity using the associative property, commutative properties to put all the scalar term to the front, and which becomes this. Okay, hopefully it's not too difficult either. Okay, the third example is I try to find, to expand this, the difference of cubes. Before we do this, inside of the cubical terms, we have some nasty looking radicals. So what I'm going to do here is I try to write them into the exponent forms. Okay, the first one is x cubical root of x squared, and the second quantity is the 5th root of y. Then subtract them, then take cube. Before I use the difference cube, the cube of difference formula, let's do something for this quantity here. We have 2 exponents, parentheses. We can multiply them out, and which becomes this, x to the power of 2/3 minus y to the power of 1/5 cube. Then I can apply the difference cube formula, which becomes this. Then once again, I'm going to use the exponent formulas to simplify each individual terms, which becomes this. Okay, and this will be the desired results for the expanding example, but I'm not going to stop here. I try to write all this nasty exponent forms into other formulations, which is like this. I try to write that. The first equality is I try to rewrite all these 3 terms into radical ones. Okay, and I'm not done yet. Okay, here I try to combine these 2 different radical forms, these 2 different radical forms into a single one, and which is this. Okay, rewrite them into different exponents, and which becomes this. Okay, so I'm putting x and y into exponents, radical ones, but taking them to the 15th roots of x to the power of 20 times x to the power of 5. Okay, these are just for fun. Okay, we're done in this step. Okay, don't worry about the other 3s. Okay, now we talk about factoring examples. Okay, we try to factor this to the difference of these 2 quantities. Okay, by observing them that they have common factor. One for scalar one is 2. For the monomial terms, x to the power of 6 and x to the power of 4, their common factor is x to the power of 4. So here are the steps we do over there. And here we're using the difference of squares to factor x squared minus 1 into x plus 1 times x minus 1. And the second example is this. We try to factor this, and 2x plus 3 times x minus 7 plus 6 times x minus 7. And by observing that these two quantities have a common factor x minus 7, so we use the reverse distributive laws to take out the common factor, and which becomes this, x minus 7, and the first term we have 2x plus 3 quantity left, and the second one we have 6 left. Okay, and the last identity there, I'm just using the associative law to deal with the first term, to add up the scalar term 3 and 6, which is 9. Okay. The third example is we try to factor by grouping. Okay. Here is the first example. We try to factor this polynomial, x cubed minus 3x squared plus 4x minus 6. Okay. What I'm going to do is group this two term and this two term together, and which is this. And next is I'm going to factor these two terms. They have a common factor x squared, and the second quantity I'm going to factor them. They have the same factor 2, scalar factor. Okay, so which is this. Okay, now observe that these two terms have the same factor x minus 3, so we can apply the reverse distributive property to take out their common factor x minus 3, and the first term there will be x squared left, and the second term there will be 2 left, so which becomes this. Okay, and this will be the simplest form of factoring this, because we cannot factor this quadratic polynomial here, x squared plus 2. It will be discussed in full later why we cannot factor them. And the second example for factor by grouping is this. We try to factor x cubed plus x squared plus x plus 1. Okay, one way to do it is group this two terms together and group this two terms together. Then do the similar kind of trick as the first one. But just for the fun of it, I'm not going to do that. I'm going to use different kind of grouping. First, I'm going to switch these two terms by using the commutative property, which becomes this. X plus x squared. I'm using the underline to emphasize the difference between the original one and here. Then we group this two terms and group the last two terms together, okay, by inserting pair of parentheses. And for the first group, they have a common factor x. Okay, and we keep the second quantity x squared plus 1, which is the sum of squares. And remember that 1 is a positive number, so it cannot be grouped for similar reason as this one. Okay, let me take out the first common factor for the first pair of, over here, the common factor is x. Okay, after we do that, I put 1 over here to emphasize on the second quantity, because as you can observe that these two terms, they have the same factor, x squared plus 1. So using the reverse distributive property. We can take out the common factor x squared plus 1, and that's it. Okay, third example is grouping, a factor by grouping. We try to factor this x squared plus 2xy plus y squared plus 2x plus 2y plus 1. For this one, I'm going to group these three terms together because they form a perfect square. Okay, and I'm going to group them, these two together, because they have a common factor 2, and leaving the third one fixed, scalar term, which becomes this. Okay, and the perfect square of these three terms, which is x squared plus y, x plus y squared. And the second quantity, we have a common factor 2, so it becomes 2 times x plus y plus 1. And after we do that, which is also a perfect square, so we just apply that result to get the final factoring answer, which becomes the square of x plus y plus 1. Okay, and now we do the factoring quadratic polynomials examples. Okay, here I'm going to only introduce the completing square techniques. Okay, the first one is we try to factor this quadratic polynomial, x squared plus 2x minus 1. Okay, the completing square technique is we try to, first, for this example, we try to get rid of, or try to completing square to make the 2x term disappear. And to do that, use the perfect square techniques. I have to add 1 on for these two terms. So what I did is I play a trick on the scalar term. Minus 3 equals to 1 minus 4. Okay, so use the associative laws to put the parenthesis on the first three quantities, and which becomes this. Okay, now the first term inside between the parentheses becomes a perfect square form, and negative minus 4, I'm going to write it as minus 2 squared, and which becomes this. And next, I'm going to apply the different square, a squared minus b squared formulas to factor them, and which is this. And then rearrange the scalar term. I'm sorry, to simplify the scalar term by using the associative laws, and which becomes this. Okay, and second example is I try to factorize this polynomial of degree 4, which is a variant of the quadratic polynomials. Let me write it down first. I put x to the power 4 to be x, the square of x squared, and I rewrite x squared into 2 times x squared, but because I'm putting identity here and original coefficient is 1, I put a 2 over there, so I have to multiply half to match the original 1, and so I have here it becomes a squared plus 2a times b. So b will be 1/2 over there. So to do that, I put 1/2 squared over there, and because the original quantity is minus 20, so to put to make the equality hold true, so I have to do some algebraic trick on the negative 20, and which is I have subtracted back to this to keep the equality holds. Okay, next I'm going to use the associative laws to put the parentheses together, and which is this. And remember that the last one is on numerator 1 plus 80 is 81, and 81 is 2 squared. So I'm putting the scalar term over there, and here is a perfect square quantity, so which is this. Okay, and that's okay. So now it becomes a difference of 2 square quantities. So I'm going to use that a squared minus b squared to factorize that into a plus b times a minus b, and which becomes this. Next, we can add the scalar term together inside each pair of parentheses, and which becomes this. Okay, the first one becomes x squared plus 5, and the second one becomes x squared minus. Here, after you do the subtraction, which actually is 4, and 4 I write it as 2 squared. Okay, for this one, again, is the difference of 2 squares. I can factorize it, and leaving the x squared plus 5 quantity fixed, because it cannot be factorized anymore. Okay, and the third example is again completing square techniques to deal with the polynomial of degree 4. Now I'm trying to factorize x to the power 4 plus x squared plus 1. However, I'm putting this example over here to show you there's a slightly different completing square techniques between this one and that one. Now I try to do the completing square technique to eliminate the scalar term, and that's how I do it. Okay, I change the x squared into 2x squared minus x. Okay, then switch this to all the two terms. It becomes, and use the associative law, it becomes x squared of x squared plus 2x squared plus 1 minus, and putting this term to the last, minus x squared. And here, the first 1 forms a perfect square, which is like this, x squared plus 1 minus x squared. And again, this quantity, I'm using the difference of 2 squares to factorize them. Okay. Now, this will be the end of the factorization technique of factoring this quantity. But to make certain that the last 2 quadratic polynomials cannot be factorized further, I'm going to use the completing square technique to check for both of them. Now I'm using the completing square techniques to simplify, get rid of the degree 1 term, x or minus x on those 2 quantities. Here it is. It becomes this as a perfect square plus a positive number, and perfect square plus a positive number. This guarantees that 2 of them cannot be factorized any further. Okay. Next topic is about the rational expressions. Okay. For rational expressions, let's introduce a quotient of 2 algebraic expressions. It's called fractional expression. Okay. For example, the quotient of 2 first example is the quotient of 2 polynomial of degree 1, And the second example is the quotient of two radicals. And the third one is also the quotient of a radical and denominator is a polynomial. And there, for the third one, I have to put a restriction that only hold true for x is not -5, because we cannot have 0 on the denominator. As for this one, x squared plus 3 will be will always be a positive number. Okay, so in particular, we reserve the rational expression for fractional expressions that both numerator and denominators are polynomials. Okay, for laws of fractional expression, the first one is the simplifications. First one is AC over BC. They have a common factor C. For fractional expressions, C cannot be 0. Okay, we can cancel out the common factor. It becomes A over B. Okay, for additions, I'm just using the simpler one identity. We try to add A over C plus and B over D. Okay, the easiest way is to change the denominator to CD, and for numerator of the first one, I multiply D over there, and you see the first quantity here is the same as, they have the same factor D. So using the simplification techniques, this pair becomes A over C. So it is the same as our original one. And so similarly for this one, we can eliminate C quantity. It becomes B over D. So we use this identity. A special case is if the denominator of two fractional expression, they have the same denominator, we can simply add a numerator. So, not using this formula. Okay, people often make mistake is when we do the addition of fractional expressions, they simply put C plus D for the denominator and add numerator, which is not true in general. Remember, don't make that kind of mistake. And for multiplications, it's quite simple. We just multiply the denominator and multiply the numerator. Okay, you should take a closer look about these two quantities. Fractional expression laws. For multiplication, we can multiply numerator and multiply the denominator together and to get the multiple of two fractional expressions. But for additions, which is we have to do something about the denominator before we do addition. Okay, and here is some examples about addition and the simplifications. For this one, we try to add 1 over x squared minus 1 plus 2 over x plus the square of x plus 1. We get the easy way one is just we multiply, get a denominator multiple. And for the first one, originally it has 1. And so because I have an extra x square of x minus plus 1 on the denominator, so I have to multiply that quantity for the numerator for the first term. And the second term, I changed the denominator. We have an extra quantity 2x squared minus 1, so I have to multiply for the second quantity. Then now we can expand the numerator, then factorize it and using the simplification techniques to cancel some common factors for numerator and denominator. I leave it as exercises for you. Here, I'm going to use different kind of techniques. First one is I factorize the first denominator, x squared minus 1, which becomes x minus 1 times x plus 1. And leaving the second quantity there. And here, next, the second step is I try to rewrite both quantities so that they have the same denominator. And for to do that, denominator, I put x minus 1 times x plus 1 squared. And from high school, we know this quantity is called this common multiple of this polynomial and that. Okay, then by changing this, I have to rewrite the numerator for each individual term. And now we have the same denominator, so I can simply add the numerator together, and that's what I do here. And then expand and add them. Okay, and this will be the simplest form for addition of two rational expressions. Okay, the second example is I try to show you the simplification of compound fractions. What is a compound fraction? Which looks like this. We have a fractional expression for the numerator, and denominator, well, I just keep it simple for just a single one term here. And to do that, to simplify this, I'm going to leave the denominator alone and do the subtraction for numerator for the first, okay, which is this. Using the same technique as above, multiply the denominator together and changing the numerator, okay? And next step, I'm going to expand the whole thing for the topmost numerator, and which is this. Expand it using the sum of square technique, the square of the sum technique, okay? And then I can, this step is I cancel the common terms. Okay, a squared are canceled. Okay, the next step is I'm going to do is to factorize the topmost numerator, and which is this. Okay, and now we have a common factor for numerator and denominator, which is the quantity h over there, and we can cancel them, and which becomes this. And this will be the simplest form for the compound fraction. So that's it. And the third example is we try to rationalize a fractional expression. Now for that quantity of the fractional expression is square root of x minus x squared square root of y over square root of x plus square root of y. Okay, so for now, both the denominator and numerators have radicals. Okay, so the first part of this example is I try to rationalize the denominator, and to rationalize that means that I try to put the denominator into a simpler form, which means polynomials. So to do that, I'm going to use the difference of square formula. So I have to multiply something. And to do that, I have to multiply something for the numerator too. And the choice I'm making here is I try to multiply the quantity x squared minus 1, a square root of x minus square root of y for the numerator, and so for the denominator. And you see this quantity is 1. And so after I do this multiplication, it is the same as the original one. But now for the denominator, I have a plus b times a minus b. So I can use the difference of two square quantities to multiply them. Okay, and upstairs it is the square of x square root of x minus square root of y. And now for downstairs, I can use the difference of two square quantity to expand that. And upstairs, I use the perfect square, the difference of the square of difference formula. And it is this. And it is this, and I can combine these two terms together as long as, okay. And the second part is I try to rationalize the numerator. Okay, so to do that, you see, for rationalizing the denominator, after I did all those steps, denominator becomes x minus 1, which is much simpler than the original form in radical terms. And now I try to rationalize the numerator. So to do that, again, I'm going to use the difference of two square techniques. Instead of multiplying upstairs and downstairs by these two quantities, now I'm going to change it to multiply the plus by changing the minus sign here to plus sign, and which is this. I multiply the plus sign, and downstairs it is the square of that, and upstairs it becomes this. Okay. After I do the rationalizing numerator techniques, the end result here is the numerator is much simpler than the original form in the radical form. In calculus, sometimes both techniques are important, so you need to learn both of them. And in calculus course, you will see when or which techniques you need to apply to do calculus problem. Okay, this will be the end of this lecture.